Hey everybody, and welcome to another video of Space Science with Python. It's been some time since I published the last video. I was on vacation, as I wrote on YouTube community and also on Mastodon and also on Twitter, but I'm back now and I think we can continue with our YouTube series. Now, before we start into today's code, I would suggest to have a quick look at the code from last time. Of course, if you are watching this video in a year or so, then a recap would be quite useless because you are in time with all the videos, but I think let's have a short look at the things we did last time. Now, last time we were taking a look at the meteors that were coming into or that were observed by a camera network system, and we plotted the radiance, so the apparent direction of the meteors on our sky map for a particular date. We also plotted 4 regions of interest. We plotted the sun, the yellow star you see here. We plotted also 180 degrees away the, let's say, anti-sun direction, so the so-called anti-Helian direction, which is here. We have also plotted the apex direction. The apex direction is the direction where the Earth is heading, and also the so-called anti-apex direction, so the direction where the Earth is coming from. And we have seen in this plot that we saw some meteors from the apex direction with a kind of high velocity. So here we see around 70 kilometers a second entry velocity, and we also concluded that these are meteors that we are capturing when our Earth is revolving around the sun. It's like a snowstorm. When you are driving with your car, you see the snow coming towards you, or rain. And it's similar, let's say, what we observe here. And we have also meteors coming from the anti-Helian direction, so somehow flying, let's say, somehow to the direction of the sun, and also other sources. We didn't see any meteors from the sun direction because this data is based on video observations and during the night. And if you want to observe meteors that are coming from the sun, you need to have radio observations, but we did not have these data in our data set. Now, the anti-apex direction is also a direction where meteors come from, but quite rarely, because these are meteors that have to somehow catch up with Earth, and then we have to observe them. These are kind of rare. Anyway, in our today's session, we would like to have a look at all these meteors from the apex direction, anti-apex direction, and so on. But the thing is that in our video here, we had to compute it for different nights. So the question is, how can we display all the things in one plot? Well, and for this, we are going to use today Spice. And for Spice, we are creating something, it's called a frame kernel. So we are creating our own reference system that helps us to determine certain this apex direction and this anti-Helian direction. Now, how does it work? Now, imagine the sun in the center, and we have the Earth here revolving around the sun. And of course, our coordinate system, if it's, let's say, fixed like J2000, the coordinate system is fixed and also points always into the same direction. Now, what we need is a co-rotating coordinate system. A coordinate system that, let's say, where the x direction, for example, is pointing towards the apex and the other vector is pointing towards the sun. And then this vector, I don't know if this, you can see what I mean. Let's say this are like x and y. So here's the Earth. It's something that rotates with the Earth. So the x vector is totally dependent on the time. And then we can convert the radiance into this reference frame that's rotating with us, and then plotting the radiance. Now, let's see how we do this. And we do this with the frame kernel I just added. It's called earth_sun.tf. Now, this kernel is stored in the main directory kernels fk, and then you find earth_sun.tf, and I would suggest let's have a look into this kernel. Now, Here we have some meta information, doesn't really matter for now, but what's important is our data here. Now in SPICE we have like the Earth, which has an abbreviation called Earth or 399. We have the Sun, which has the number 10. We have the barycenter of the solar system, which has the number 0. So if you don't know all about this stuff, in my general tutorials I did some things about the SPICE and also the kernels, but let's have a look here. We have a lot of different definitions here for our frame, and I just call the frame now Earth underscore Sun. I give it also some artificial number here, 1400 10 3 1 0. You can choose anything that's not already being used, and it is a reference. It is a coordinate system that has the ecliptic J2000 as a reference system. Cool. Now, how do we define it? We define it using it two vectors. Yeah, so it's a so-called third-hand rule. If you define an x and a y vector, then the z vector is orthogonal to perpendicular to both other vectors. So you just need to define two vectors. And it doesn't matter if it's x or y and z or so, it really doesn't matter. I choose the following definition. The y direction is, the y direction points from the Earth to the Sun, and the z direction is basically the, let's say, north pole of the ecliptic plane. Yeah, and why do I do this? Well, we will see in the plot. I want to have the if we just make the hand rule x, y, and z, I want the apex into the direction, or the x vector into the direction of the apex. So if I compute the radians and the longitude, I get for the apex, best case, longitude and latitude 0, 0. So if we make a sky map, then the apex is in the center of our sky map and not shifted 90 degrees or at some edge corners of the plot. So the apex I would like to have in the center, but you can define it as you like it, because there's like no definition for this. This is like our kernel, and there's like no, let's say, standard that defines it. Now the z direction here, as I said, is the let's say north pole, and it's simply a vector with, which has the value 0, 0, 1. So the z vector is component is 1, and it is it corresponds to the so-called ecliptic J2000. Now, if you define kernel a frame in SPICE, in some frame kernel, and these two vectors are not perfectly perpendicular, it will try to make the closest approach or assumption how these two vectors may look like. So be always careful that you can mess things up. Let's move to the code, I would say, and I called this here rotating Earth and Meteor project sporadic meteors, where we have our space kernel called Earth Sun TF. Now, the first cells are basically the same as last time. We read in our data, we filter it a little bit, playing around with some stuff. We add also the date time and also the day of year. Isn't really useful in this case, but it's just a copy paste from last time. And we read in our space on our SPICE kernels, and one is the so-called Earth Sun TF. Now what we do is we need to convert the radians now from ecliptic J2000 or J2000 to, in this case it's J2000, to our new, let's say, Earth Sun co-rotating frame system. And we do this first by creating a function, and this function is being used to conduct this conversion. So this is the name of it. It's called J2000 to Earth R. That's just the name. And what we do is we take the radians values and the declination values, so longitude and latitude values. We put them into this SPICE function, and it converts the sky coordinates into a vector, three-dimensional vector, x, y, z. Now we compute here a matrix that converts between J2000 and this Earth Sun system. And this conversion, so it will provide a transformation matrix. So we have to apply this matrix to our original vector of our J2000 radians. And this is time dependent. So this is why we have here the ET value. And this is the reason why we have to compute or execute this function for each individual meteor. Of course, within a day, it's not a lot of changes, but if you want to be highly precise, then you have to do it for every nanosecond, basically. So this is what we do here. And then we apply the matrix on our vector. We get a new vector that is now our radiant in this co-rotating frame. And then we convert it back into the new radiant and declination values we have here at the end of our function. And this is then returned, and then we can write it into our data frame. So this is basically the function here. This is now being applied here in our data frame. Apply function, where we use the radiant, the right ascension, the declination, and the time, and then call the function, and then write here the two columns. And then we need, of course, also to convert it we need to convert it for our matplotlib plot. Now let's plot these things. We have the same functionality as last time. We basically copy paste, but this time, of course, with another column with this right ascension of Earth R, and Earth R red. So these two columns here. We apply our let's say plot design and everything, and then let's have a look now at our final plot. Of course, I also applied an alpha value for all the radians, 0.03, because we have thousands of dots. So let's see now how the plot looks like. That's the plot. And what do we see here? What are the different regions? Here at 0, 0, as I said, we have the apex direction. So the direction where the Earth is flying through space. Now, if we go 90 degrees to the right, 90 degrees for 24 hours means it's 6 hours. So from 0, 6 hours to the right, it's now 18. So the right ascension is 18 hours. And we see here our other, let's say, blob of information. And then this is our anti-Helian direction. And our Helian direction is here on the left side. And as you see, it's kind of dark, no data at all, apparently. Or is it? Yeah, maybe, because we have set a high transparency value and maybe it just vanished in all this huge plot. Now we see there are different regions. We see here, of course, the apex part. We see here could be like a void or something that is circular around it. We have here maybe something brighter, could also be a meteor stream. We see some streams here. We have, of course, our region here. So how does it look like? What are the sporadic sources? And for this, we can switch now to a source from NASA, which is shown here. The plot, unfortunately, is a little bit low resolution, but I think you will get the gist. Now, NASA says that there are in total 4 different sporadic regions. The first one is the Helian anti-Helian direction. So in our case, it is this direction here, the anti-Helian direction. Then we have the apex, which is separated somehow in the north and south apex. So it's somehow separated. They're like apparently 2 sources. In our case, we don't really see it. Yeah, maybe you see it a little bit fainter than on the top and bottom, but let's skip it for now. And then we have something called the toroidal source and also the asteroidal source, which goes really close to the higher parts of our declination values. And we may see this here. We have some bluish dots here. We have also here a small ring. So we don't really see it like here, but we get an understanding. But to be honest, we also get somehow a biased feeling how this could look like. I mean, we are now biased because of this one from NASA, but can we see it also in our data? So the question is, what do we do next to get a better view of the sporadic meteor sources? Well, for this, I would suggest we will next time we will use a kernel density estimator to get a better plot of our data points, because now we have some transparency values for our scatter plot. We can change it, then of course the plot will change. You can try it out, of course, use different colors, and you will see, well, based on how you manipulate things, you will see different, let's say, regions of interest. So I would suggest let's make some density plot out of this, and then maybe we can also apply logarithmic scaling or so that we see also fainter regions that are then more prominent. On the other hand, so this is like what we do in the next video, I would suggest, and you can maybe start doing it now if you like. I did some previous videos on this topic, so take a look if you can do it. The overall goal would be like to see only the sporadic sources. So we have to remove the meteor streams. And this is, if you recall, our original idea. We want to identify the streams, classify them with a machine learning algorithm. So this is what we will do then afterwards. We will create some machine learning algorithm to see where are the sources, which meteors belong to a stream or so. Then we will hopefully separate it into the different streams and also hopefully into the sporadics, or let's say the background. And then we apply it, we filter things out, and then we do the same thing again without the meteor sources and see if we can see the structures. And then we can use again machine learning to find structures in the data. Yeah, and these machine learning algorithms, they exist in astronomy. They are being used by astrophysicists, for example, to get an understanding and feeling of the galaxy, of the bigger galaxy structures in the universe, like what kind of net is being built up by superclusters and so on. And this is something similar here, but with meteor data. Well, I hope you learned something today. I hope you are eager to see what we will do with the meteor data. If you hear in the future some news about sporadic meteors, then you will now get an idea and understanding what they are. They're not associated with actually with a stream coming from meteor or asteroid, but more coming from, let's say, a broader region of interest, like the apex or the anti-Helian direction. That's all for today. We'll also throw in some more videos about science stuff. I would like to talk also about Helian sources, but I don't have the data, so at least I would like to provide some scientific videos about this. Let me know what you think about this, and until then, happy coding and see you next time.